யூடியூப் மானிட்டர் பண்ணிருப்பீங்களா?
Yes, sir.
Sir, I will monitor the YouTube, sir. Don't worry about that. I will monitor the YouTube.
இல்ல நான் இப்ப கொஸ்டின் முரளி போடுவாப்லையா இல்ல முரளி நீங்க அங்க யூடியூப்ல ஒரு கொஸ்டின் எடுத்து உள்ள போட்டுறீங்களா நம்ம சாட் பாக்ஸ்ல?
Murli, you need to do the in YouTube we receive the questions regarding this meeting, da. So we need to take that questions and we need to place the questions in the chat box.
Okay.
Okay,
So
Murli,
you
open
open the YouTube.
Hello. Brother, whether the live is going on, huh? YouTube live is going on. No, it didn't yet start. Hello.
So,
Brother, whether the live is going on, huh? YouTube live didn't yet start. Hello. Brother, whether the live is going on, huh? YouTube live didn't yet start. Hello.
Kanagaraj, please make myself and Naveen as host.
the live is going on. I started the live.
welcome you, sir. Hello, sir. Welcome you, sir.
Hello, everyone. How are you?
Welcome, sir.
Nice to see you.
Hi, Samir.
Hi.
Hi,
Good
Samir.
evening.
Welcome.
Good evening there. It's early morning here, so the other side of the world, right? So just
Hi, Samir. I'm Navneet. I'll be
Hello.
the host for today. Nice to meet you.
Just to be sure, how much is my presentation time? The time I'm allowed to present?
25 minutes.
25.
Yeah.
Okay. I had prepared a little bit more, so I'll try to make it shorter then. $25, right?
Yes.
Okay. Let me just then.
Team, shall we start?
Whenever you're ready, I'm ready.
Good evening to all present here, dear scholars and participants. Welcome to the first online session of the iGen I Explore Sustainability Research Lecture Series. We are excited to have you join us virtually as we kick off this important initiative to explore groundbreaking research and innovative solutions in sustainability. Today we have got an EV man with us. iGen, to say about iGen, the Institution of Green Engineers is deeply committed to advancing sustainable development through many sessions on research, innovation, education, and collaboration. The iGen I Explore Sustainability Research Lecture Series is a monthly event designed to connect scholars, researchers, and global experts. Each month, we host a leading expert to share their insights on various sustainability topics, fostering a global knowledge exchange and collaborative efforts toward achieving the United Nations Sustainable Development Goals. We are also proud to be associated with the I Explore Foundation for Sustainable Development, which plays a crucial role in supporting this series and our shared vision of a sustainable future. Today's session will be moderated by Mr. Navneet Krishnan Ramanathan, the director of I Explore Foundation. He will be guiding today's discussion, ensuring an engaging and insightful experience for everyone. Thank you for joining us today online. We hope you will find this session enriching and are inspired to take action towards sustainability. Over to Navneet Krishnan Ramanathan.
Thank you, Dr. Akhila, convener of iGen I Explore Research Lecture Series and Secretary of iGen for setting the context and explaining the reason behind this wonderful initiative. To say about iGen, as Dr. Akila said, iGen connects green professionals worldwide working towards SDG goals and providing solutions for a sustainable greener future through 9-color nanogon WIBGR society. iGen is an UNDESA NGO. It is a 12A ATG and CSR registered organization, also accredited by NITI Aayog. It has initiated various programs to engage with the universities, institutions, and organizations to promote the green. Today, for this program, we also collaborate with iExplore Foundation. It is a community impact organization envisioned to impact 1 million young children on responsible technology as path to achieve sustainable development goals. Empower youth to build a sustainable world through augmented social innovations with science and technology. iExplore is a non-for-profit organization registered as a Section 8 company under Ministry of Corporate Affairs, India. It is 12A ATG and CSR registered company and also accredited by NITI Aayog. iExplore is impacting the students through various programs like IEEE Assist 12 in partnership with IEEE, which is the world's largest technical professional society, and its flagship program, Returning Mothers Conferences with World Bank and Cyber Champions with Rotary International to give an awareness about cyber crimes and issues for the young children. And it is a nodal agency for a program ATL Sarthi along with Atal Innovation Mission. Friends, today's lecture is on electric vehicle charging technologies. And as Dr. Akila told, we have an EV man, Dr. Samir Kauro. Samir received his MSc and PhD degrees in electronics engineering from Universidad Técnica Federico Santa Maria, Chile in 2004 and 2008 respectively. He is currently working as an associate professor and as a research fellow at Universidad de Sevilla, Spain. He held key leadership roles in universities, including Director of Innovation and General Director of Research, Innovation and Entrepreneurship. His research focuses on power electronics, renewable energy systems, green hydrogen, and electric mobility. Dr. Samir has directed 44 research and development projects and is founding member and principal investigator of the Solar Energy Research Center, SERC at Chile, and deputy director of the Advanced Center of Electrical and Electronics Engineering. He has authored over 200 papers, 2 books, and 14 chapters, and served as the guest editor in various IEEE journals. Dr. Kauro has received numerous awards, including highly cited researcher recognition in 2018 and IEEE AIE Outstanding Engineer Award in 2018 and several IEEE Best Paper Awards. He is also an associate editor for the IEEE Industrial Electronics magazine since 2022. It is a great pleasure to have such an eminent researcher and an engineer to talk about the EV electric vehicle charging technologies today. Presenting you, Dr. Samir Kauro. Over to you, Dr. Samir.
Well, thank you very much for the invitation. I'm very glad to be part of this event, and I certainly would like to thank you and the people attending this seminar online for their time. So without the further ado, I think I will try to load my presentation. Just let me know if it's visible.
Yes.
Okay. So are you seeing the presenters slides or the full slides? I'll just do like this. I think now you're looking at the right slide, right? Okay, great. So thank you for that kind introduction and the invitation. I will talk to you a little bit about electric vehicle charging technologies. My background is in power electronics, so if you work in power electronics, it will make more sense to you. If you don't work in power electronics, I will try to keep some of the language um, as general as possible so that you can follow as well. So I come from Valparaiso in Chile, and this is just to show you where I'm from. It's in South America, in the Pacific Ocean, in front of the Pacific Ocean, and this is our university, and next to the university is our research center, AC3E, and these are some pictures of where I work. So it's a nice setting in front of the ocean. In case you come to Chile, into Valparaiso, just let me know. I suppose my contact has been shared, so just let me know and I can show you around. I will talk to you a little bit about an introduction, then EV charging infrastructure, charger topologies, and grid integration of chargers and what we could do with the grid, and then some challenges and future trends and research topics. Just in case you would like further reading, a lot of this presentation is included in this paper that we published in 2022, in 2021 actually, which is strongly focused on the power electronics side of the electric vehicle charging infrastructure, and this other one published last year in the IEEE proceedings, which is focused a little bit more on the grid integration. But both papers include contents of what I'm presenting here today in case you need further reading or get into more depth. So the issue is why we're electrifying transportation is because of climate change. Climate change is caused by greenhouse gas emissions that come from burning fossil fuels, and transportation is directly responsible for 14% of that. So this is forcing an energy transition in the sector and by electrification of all means of transportation. So that's why you probably have been hearing about electric buses, electric trucks, even micro electromobility or urban electromobility, industrial electromobility, and so forth. But for the purpose of this presentation, since we have a window of time, we are going to focus mostly on battery electric vehicles and plug-in hybrid electric vehicles. So how is the transition going? So the transition is accelerating. As you can see, we have an exponential growth in electric vehicle adoption around the world, but still, it's just we just cracked 40 million electric vehicles last year, most of them in China, as you can see as well, and it was 18% of the car sales. So 1 of 5 cars was electric among the cars sold last year. And this has been a good increase respect to 2022. It's also showing a 30%, 35% increase on a year-by-year basis for the last 10 years. And there is a global car stock of electric vehicles of 3.2%. So among all the cars on the streets, just 3.2% are electric. So this is an interesting growth. Nonetheless, it's still lagging behind of what we would like. And so this makes us look at which are the market barriers. So why are electric vehicles not as much as adopted as we would like? And then you will see the suspicious the topics that are the suspicious ones, like the vehicle cost, range and autonomy, maintenance, standards and regulation, charging infrastructure, charging time, and cultural change. So among all of these, I will just skip to the summary. Vehicle cost and second market value are really improving to a point in which we can now, in many economies, I'm not sure what's the case in India, but in many cases around the world, owning an electric vehicle has the same cost as a non-electric one over a 5-year span. So you get a return on investment because of the lower maintenance. And range is also not an issue for most of the cases, since people use their car mostly to go to work and maybe to driving around the city. So in most cases, range and autonomy is enough. Much like our cell phones that we charge every day, if we get used to charging our car every day, we're good to go. When we get into standards and regulations, then we see that there are multiple standards across the world. Some of them are incompatible among each other. Charging times still remain, for some people, a problem that you have to charge overnight, for example, or if you have a fast charger, you end up using 30 minutes, which is longer than we have with internal combustion engines. And there's still a cultural change in some places where electric vehicles are perceived as not as powerful or not as good as internal combustion engines. But the main problem is actually charging infrastructure. So people believe because they don't see the charging stations on the streets like they do see the gas stations on the street, they perceive that they could have, you know, a lack of energy at some point and have and get stranded, and which is called range anxiety. And here you can see that there is just a little bit above 2.5 million slow chargers around the world, most of them in China. And if we go to fast chargers, we are below 1.5 million. And there you can really see that only most of them are just in China and in Europe. So yes, the charging infrastructure, particularly fast charging infrastructure, is a problem in those places where you have long distances between cities and where you would need such an infrastructure. So here are the three main types of infrastructure. So slow charging at home, which is with the charger you have on your vehicle. Then you have AC fast charger or medium range fast charging, which is for opportunity charging when you know you're in a mall, in a shopping center, maybe a supermarket, or you park on the street. And then you have range extenders, which are the fast charging stations that are more intended for highways, right? And if you look at charging technologies, we would find that we can find all of these plotted in this graph. So the dashed line is what's the border between what's on board the electric vehicle and what's off board the electric vehicle. So in this case, we have onboard chargers. So these are chargers that are included on board the vehicle. They are usually low in power because of their size. They need to be on board the vehicle, so they don't go over 20 kilowatt. Usually most of them are around 6 kilowatts. So this is what's called slow charging and what you do at home. Then you have when half of the charger is outside the vehicle and half of the charger is on board the vehicle, and this is wireless charging. We will get to wireless charging more in a bit, but the problem here is the lack of standards and infrastructure in the cities and highways to actually charge wirelessly. Then you have off-board charging when everything is off-board the vehicle. So these can be large chargers. They are usually DC because they can connect directly to the battery. So these are rated between 50 and 300 kilowatts, and they can charge your vehicle from anything between 45 minutes to 15 minutes, depending on the power of the charger and also some conditions on your battery and your vehicle. And then you have completely everything off board, including the battery, and this is battery swapping. This is when you charge the battery off board and then you arrive with your car and you just swap your depleted battery for a new battery. So these are all the charging technology types, and here you can see how they are added in a classification with respect to the standards. So in red, orange, you will find the AC charging standards, and in blue, the DC fast charging standards. And because DC fast charging is faster, it's higher in power, you will see all of those to the right, where you can see that they can reach from 100 to 400, 450 kilowatts in power, while low AC charging is at the lower end. I won't go into detail around the standards, but you can find those in the paper I mentioned at the beginning. Here you can see both AC standards with the AC connectors, and here you can see Tesla standard, the one from China, and the one from Europe. And then here you have the DC fast charging standards, typically the ones in Europe, CCS2, and then in China, GB, and in the US, you have a lot of Tesla chargers. To demos from Japan. So here you can see the power ratings, voltage ratings, type of region in which they operate, and so forth. In one of the papers, we also go into very much detail on the different power converter topologies that we use for each of these stations. So again, in red, you will have AC chargers, and in blue, the DC fast chargers. And here we have added a new category, which is integrated chargers. These are AC, so they connect to AC networks. But basically what they make use of the powertrain of the electric vehicle. So they use the motor, they use the inverter that usually drives the motor to actually charge the battery. So it's not a dedicated charger, as in the case of the onboard chargers that are The only function they have is just to charge the battery. So integrated chargers, you use part of the electric vehicle as a charging station as well. And therefore you get higher ratings. So I just will bring some examples, just one example of each to see in a little bit more detail, but a little bit more on those technologies. So the onboard charger needs to connect to the AC grid. It's usually single phase. You can either have bidirectional so that you can supply energy also back from the battery to the grid, but most of them are unidirectional that take power from the grid to the battery. So they use a passive diode front end, and then they have a DC-DC isolation stage to have galvanic isolation between the battery and the grid. So that's a generic case overview. They usually look like this in the vehicle, so they are located within the vehicle, and it's of course a small box like you see over here. And outside of the vehicle, you have just the connector, which is a special cable with a special connector for the standard you have, some protections, and maybe some power measurements. But what you see outside of the vehicle, it's not really a charging station. It's just more like a human machine interface rather than a real charger. The charger is actually on board the vehicle. You have these topologies over here. I won't go into much detail on those for the moment, but you can see that these two over here are of passive nature, so they just take power from the grid to the battery, while the two on the bottom have bidirectional capabilities, so you can also do electric, so vehicle to grid, which is deliver power from the vehicle to the grid or from the vehicle to any other tool or thing that you would like to power at your home. This is one example in more detail. This one is the Tesla Model 3 and Model Y onboard charger. As you can see, it's rated from 11 to 22 kilowatts. It has 95% of efficiency. It's composed of several modules in parallel to reach that power level. And it's made of a single phase reconfigurable to three-phase active rectifier, and then followed by an LLC resonant half-bridge DC-DC converter. If you go to the integrated EV chargers, these are the ones that use the machine or the motor to actually be part of the charging process, as well as the inverter that is used in the powertrain. So basically what they use is they use the coils of the windings of the machine as an inductive filter, which is then reconfigured through switches to be able to drive power from the grid to the battery. Here we see 4 examples. I'm just going to show you one in a little bit more detail. This is one from the Renault Chameleon. This is a French car. And so here you can see how they use an IGBT rectifier, and then they use the inverter in the machine to actually, they use this one to boost voltage, and then this one to control the battery voltage. It's rated 44 kilowatts. And then if we go to DC fast charging stations, then we have the case in which we have a low frequency transformer. It's shown here very small, but it's actually rather big, which is over here. Or it can have a high frequency transformer, which is over here at the DC-DC stage. And we can have also the same configuration for buses. So this is what is being used for buses and trucks. And you can have depot chargers where the bus is stationed for 45 minutes an hour, or you can have opportunity chargers where you have a catenary going up to actually pantograph going up to a catenary to actually charge when the bus is driving, or when the bus is stopped over a small amount of space, right? And usually these fast charging stations are not single units. They come by many. So like a gas station, you have several charging points. And in many cases, 2 charging stations can be actually connected in parallel, so you can drive more power out of one. Here you can see the case with high frequency isolation. This is the case with low frequency isolation. And these two are where you have an AC bus configuration, so where the AC is common to many charging stations. Both have galvanic isolation for each one anyway. So you have here and here galvanic isolation. And then you have the DC bus configuration where you have one large AC-DC rectifier, and then followed by many DC-DC with high frequency isolation charging points for each vehicle. These are some examples of these topologies used for off-board chargers. You can find more detail on those in the papers I gave you at the beginning. But I will show you just the Tesla Supercharger version 2. This one goes up to 135 kilowatts. It's made of 13 power electronic building blocks made of 3 phases. So it's actually 39 of these units you see over here. It's made of a single phase rectifier followed by a boost converter, which elevates voltage. And then we have full phase shifted full bridge to regulate the battery power. Now we get to the vehicle to grid or interaction with the grid that you can do with your vehicle. So current vehicles are actually in this first level, so grid compliant and controlled. So this is what you can actually do today with vehicles. We hope in the future we can get to fully bidirectional and aggregated charging, which is when actually, for example, a fleet of vehicles, a bus station, or a parking lot can actually feed power back to the grid, and the grid can regulate and control the battery packages to optimize the grid and have complementary services like energy shifting, peak shaving, and other kinds of stuff. But for the moment, although some vehicles are already bidirectional power flow capable, some regulations around the world are not that far advanced. So basically, most of those vehicles, what they can do, they can share power with the home, but not really with the utility. In one of the papers I showed you, we actually explored what these technologies, these charging stations can actually do for the grid. So this is looking more into the future. So how we could actually provide more complementary services to the grid, like say like phase imbalance regulation, static compensation, inertia, provide inertia, grid forming, and so forth. And so this topology over here, when connected to the vehicle, cannot perform any of these, for example, because it has a passive front end, so it's not bidirectional. And when we disconnect the vehicle, even less. But if we get into these more advanced topologies, you can see that even without the vehicle, which is the case of the one here, when you see the vehicle in gray, when the vehicle is not connected, you can also provide services, which is great because then even when your charging station is not being used by electric vehicles, it's providing services to the grid, and these services could be monetized, and that could become an incentive for people actually producing fast charging stations. And that would make one of the problems I showed you at the beginning, the lack of charging infrastructure, improve, right? And of course, with the vehicles, you can provide more of these benefits because now you have the battery, so you have energy stored and you can do more stuff. In this slide is just a continuation of the other one for other two topologies. In the case of single phase, 3-phase, with vehicle, without vehicle, and all the things you can do to support the grid. So that would be a very interesting idea, both in terms of research and also public policy to advance regulations in order to be able to do this stuff. So we can actually make more use of our charging infrastructure just than charging cars. Then other trends in the present and future is that batteries are getting higher in voltage. So now we are vehicles used to get up to 400 volts. Now we're getting vehicles to 900 volts, which is allows faster charging. It allows higher efficiency and better power density. So it's very good for the industry. But the problem with that is that we now have another new standard, of course. We have to reach up to 900 volts with the battery chargers, and the charging infrastructure that was already there was probably not capable of doing 900 volts. So we are back again with this discrepancy between some vehicles and what the charging infrastructure has. So there are some R&D opportunities there to do retrofitting to existing charging stations or new charging stations capable of doing all standards, 400 volts and 800 volts batteries. Wireless charging is also a trend in research. It's not really available commercially or mainstream, but lots of people say it makes a lot of sense, particularly because then you can reduce the size of batteries and we can reduce the cost and weight of the electric vehicle by having smaller batteries, and then we can supply the extra range on the highway, which would be dynamic charging. So the being able to charge the vehicle when it's moving. We can also have static charging, which is wireless, but when the vehicle is parked, and that would also extend the range, but more intended for city use, right? But really to reduce the battery, dynamic charging, so on the highway, that would be the way to go. The problem with this is that it has a lower efficiency, so transmitting power through the air is less efficient. It has, of course, a larger cost because you have to invest a lot of infrastructure in highways and cities, and that's why this idea is a little bit slower in development than normal chargers. Another trend in research is chargers for heavy duty, and the idea here is to get into the megawatt charging range. So instead of 400 kilowatts, surpass 1 megawatt. In fact, the megawatt charging system, which is championed by Charing, which is a global organization of companies that are working together to form a new standard. They are pushing for charging stations between 1 and 3.75 megawatt in charging. And the idea is, of course, for trucks and buses, but this will also probably benefit for electric vehicles in general. So that's also and that's the connector over here that they are pushing forward. So this is also an area of research. People are like researching into these topologies and architectures to reach these power levels. Battery swapping is also making a comeback. So battery swapping was actually proposed a long time ago, but only very few car manufacturers are actually doing it and doing it well. The one that is most known for this is NIO from China. So NIO has battery swapping stations where you can just go through with your vehicle. You stop for 5 to 10 minutes, takes the depleted battery out, and everything is done automatically. So no human intervention whatsoever. And then you take a charged battery and then you're good to go. The problem with this is that you need redundant battery in the system. So you need to have batteries on the vehicles on the streets, and you need also batteries in the charging stations being charged. So compared to wireless charging, instead of reducing the amount of battery needed, it actually increases the amount of battery needed. You could make the case that, well, you can reduce the size of the battery if you're going to swap it from time to time, but this is not what the industry is going for at the moment. And perhaps the best case for battery swapping is actually for vehicles that are working the whole day, like Uber Eats and all these delivery motorbikes and electric bikes, which are working, and also maybe taxis, because you have to work the whole day. You're not, it's not in a good business having your car parked or your scooter parked for 45 minutes or 1 hour while you're waiting to be charged. So here battery swapping makes a lot of sense. So for working vehicles, so vehicles that have to be on the road during a long time of the day without stopping for charging, large time battery swapping makes a lot of sense. So the final technology I'll bring for today is partial power converters. So partial power converters are power converters that just used a portion of the power. So that's what the names comes from to charge the battery. Actually, they use a full power, but they process just a fraction of it. So here you would see a full power converter. So if this one is rated 300 kilowatts, and then this one is also rated 300 kilowatts. While in partial power converters, the DC-DC stage can be rated at a third of what the AC-DC stage is rated. So this one could be, for example, rated just at 100 kilowatts. So this is lower in power, lower in volume and cost, and therefore also lower in losses. We have done some developments in my university on this technology, and we have reached very high efficiencies, 99.035% of efficiency. We have now made a new module for this for a company in Chile that charges buses. So this is a 20 kilowatt unit that is supposed to be connected 5 modules in parallel to reach 100 kilowatts to be able to deliver 400 kilowatts to each bus. So here you can see the designs, original designs, and then these are the physical units being built of this 20 kilowatt DC-DC converter module. This will be used in the Santiago bus system, which is the capital of Chile. So the conclusions are that the market is not fully developed yet, and it's not global deployed in terms of charging infrastructures. Despite the great advantages, we still need to reduce the variability in relation to different charging standards and charging structures to have a more mature technology that can benefit from increasing the scale of production. And then, of course, there are a lot of trends in R&D, like wider voltage operating range, getting for 400 to 900 volts, higher in power, increase efficiency, power density, and particularly increasing reliability. So we need these stations to be operational as much as possible and without failure because they are part of the infrastructure. And also, this would be even more critical when we do grid integration, which is this complementary services I talked to you before. So the main conclusion or the main takeaway is that there is plenty of room for R&D and technology transfer for the next decades in relation to charging infrastructure. So with that, I conclude my presentation, and of course, I'm open to any questions you may have, should I be able to respond them.
Thank you, Dr. Samir, for a detailed and insightful presentation about EV charging technologies. In fact, EV charging ecosystem is one of the influencing factor for EV adoption. Today, almost all the countries are, promoting the EV like anything. As a user of EV, the first thing comes to a user's mind is how about the charging infrastructure available in my zone, in my area. Lot of high quality researchers are happening across the world, and good to know through your presentation about the next big things going to happen in the EV charging and technologies. Thank you so much for the session once again. I have a couple of questions which this presentation is also going online YouTube, and I have noted a couple of questions from the attendees, participants. Let me put forth. What are the key challenges in developing a widespread and reliable EV charging infrastructure, especially in emerging markets? And how can these be overcome through innovation in charging technology? This is from one of the scholar working in this power and energy related to EV.
Oh, that's a great questions, and there are many answers to that question actually. So there are many challenges. One of them is the amount of standards, of course, and that you have. For example, in Chile, where I live, we get vehicles from the US, from Europe manufacturers, but we also get vehicles from China. So we had a lot of Chinese vehicles, and all of them have different charging standards. So that's one issue. So having if you are going to build an infrastructure, it needs to have all the standards, or you need to put regulations in place that enforces the standards to actually work together. This is happening right now. So I don't if you probably heard Tesla is now allowing CCS chargers in US to be compatible, so you can charge your Ford truck on a Tesla supercharged network. That was not possible a few years ago. You could only charge Teslas on a Tesla charging network. So compatibility is, of course, one issue. The other issue is reliability. So power electronics is rather a quite new technology compared to other technologies. So it started really in the 80s and developed quite firmly in the 90s, but still chargers tend to fail on an 8% rate. So if you have 10 units charging, probably one unit is not working, not operational, right? So if you arrive to a charging station, you will see one of them down, not working, either for the power electronics or the interface, or even nowadays, there is some vandalism as well. In some countries have been reported people stealing the copper cables now that the copper prices are up. So they're stealing the copper cables that go from the charging station to the electric vehicle. So this might be not heard of in the US and Europe, but this is happening in other economies. So the availability of the charging station is also a challenge. And another challenge is the fact that electric vehicle manufacturers are also switching from 400-volt batteries to 900-volt batteries. And even now, some manufacturers are thinking of going to 1,500-volt batteries. That's very good in terms of efficiency and charging times and everything, but that puts, again, new stress on the charging infrastructure because of course, everything that is already installed won't be able to meet the new batteries. And also, power electronics is not the best technology to increase voltage or reduce voltage. That's transformers. So because we need power electronics to actually charge the batteries, if we add more transformers, it increases cost. And if we do the different levels of voltages with power electronics, that will reduce efficiency. So so the requirements that are needed to be able to cater to different battery voltages is also a huge challenge. And the last, but perhaps biggest challenge is the fact that most people need to see the fast charging stations on the streets to actually make the commitment to switch to an electric vehicle. But then when they have the electric vehicle, they never use the charging station on the street. They basically charge at home, much like you do with your cell phone. So maybe you remember at the beginning when you first switched to a smartphone, you would find some chargers in some shopping malls and shopping centers where you can charge your phone. You can see them still in the airports, right? But most of the people just charge their phone overnight. And the same will happen or is happening, for example, in Europe with most people that have an electric vehicle. So they charge at home overnight because it's convenient. You just don't waste any time. You get home, you switch it, you put it to the wall and it's charging. And then in the morning, you're good to go. So you don't have to actually spend time getting into a station either for like you needed to do with the internal combustion engine. So this is putting some pressure on the people owning charging stations because they cannot monetize or they cannot get their investment back in a short term because they get the return on the investment by selling energy to the electric vehicles. But if no one is charging or the electric vehicle charging station is empty most of the day, the payback is in 9 to 10 years. So there's why investing? And this is why you see such a little amount of charging stations around the world. So and that challenge could be overcome by this idea we put forward in this paper in which we say, okay, but then you can monetize your charging station, not just to do charging of electric vehicles, but actually provide other services to the grid. And that monetization could make the business more attractive.
Thank you, Dr. Samir. I think you just put a light on some of the areas where an aspiring researchers in this domain can look up to. Great. The next question from Dr. Kanagaraj is, what are the pins in charging connector of an EV?
Okay, so the connectors are, as you could see in one of my slides, I will see if I can put it back again. Sorry. So here, I guess now you're seeing, right? So here you can see all these pins, right? I think that's what's the question is referred to, those pins. So in some cases, the pins are the connect, so is actually the power outlet. So in this case, these are the two pins for DC, and these are the pins for AC charging. So this CCS1 connector does both. And also you have also pins for communications, which is other data that goes between the electric vehicle and the charging station, which is called a handshake, in which the electric vehicle lets the charging station know the state of charge of the battery and some other conditions of charging that the vehicle is allowed to do. And so that information goes back and forth to and also to test, for example, if there is any leakage current going to ground that could make would be harmful for the equipment or the people. So there's both power going into those connectors, and those are the pins for it, and also data. So both kinds of information go through these connectors. and the why people made different ones, it's the same what happened when you see the normal outlets and difference between a connector, you know, a normal plug you see in the US, which is with two spades, and then if you go to Europe, it's with three round ones. So every country may make initially a new connector because the technology is being developed, so everyone is original about it. And then it's also a way of protecting your country or region's development of a particular technology, so the other technology doesn't come earlier to your region, and then doesn't allow the industry in your country to grow, right? It's a way of protecting the economy of local economies to be able to be part of the development of the technology so they can grow before another country comes over and deploys their technology. And then we have only, let's say, Chinese charging stations or American charging stations all around the world, and makes it a monopoly. So that's why standards are different.
Thank you, Dr. Samir. The next question is, what is the minimum guaranteed life period of a battery? The durability, minimum durability of a battery
Yeah.
that we.
So that varies between manufacturers. Now, one of the studies that I have referenced in my presentation from IEA, which I strongly encourage you to look into, the one of 2024 just came out, which is the Global EV Outlook. There you can see some data on that. And so the average warranty for batteries today is 8 years or 130,000 kilometers. So the the notion that batteries would just last 1 year or 2 years is actually not that accurate anymore. So batteries are actually warranted for 80 years or even 130,000 kilometers. That's the average. So that means some manufacturers will do more, some manufacturers would do less.
Great. The next question is, can the EV batteries be recycled?
Well, yes, the short answer is yes, but most things can be recycled. The thing is it cost effective? So that's the main issue, right? So if something is not cost effective, if people won't do it, and if people won't do it, then it's not sustainable. Sustainable has to be not just good for environment, it also has to be good for the pocket. So if people cannot do it, it won't be done in the future, and therefore it's not sustainable. So the thing right now is that we're looking into two things for batteries. One is to not just recycle the battery. So first, we would like to see how can we use the battery for a second purpose. So first purpose, serve it for a couple of years in an electric vehicle. And then we call it second life use of batteries, which is repurposing them for other uses. So maybe it's not good anymore for a vehicle, but it could be good for a power plant or a distributed generation with or for a home connected with the PV system. So that's called second life battery use. And that's the way to go, because that's making more use of the same battery, and reusing is of course more is a first stage before recycling. And then comes recycling. And I'm not an expert on recycling, so I won't give you a lot of details on that. I know that this is now being researched in terms of there is not a single word. Some people are doing a recycling of batteries, but there is not like a mainstream solution or a world-leading company doing that. So I think that title is still up for grasps. So if you do some innovations in which you can streamline the process for different manufacturer, different cell types, different cell technologies, and you can do that cost effectively, of course, that's a big win if you would like to look into that.
Wonderful. Dr. Samir, the next question is related to green hydrogen, as you have also worked extensively on green hydrogen. How do you see the synergy between hydrogen fuel cells or electric vehicles? How do you feel it will, whether the green hydrogen fuel cell will take a lead after EV, or will it go hand in hand, or will there be a hybrid hydrogen-based EV vehicle kind of things? What do you think about?
Yes. Well, so that's also a very good question. I think green hydrogen as a more generic thing, like an energy vector, is going to be big. But I don't think that it will take over in the short term, in the next 30 years, the electric vehicle, the use for urban electric vehicles. So if you saw my slide, I showed you other electrification of transportation like trucks, buses, ships, and so forth. And I said that today we were concentrating on electric vehicles or urban electric vehicles. In that case, the development of batteries is going so well and is going so fast, and new technologies are coming, and solid state batteries are also coming, that probably by the time the hydrogen infrastructure to produce hydrogen, distribute hydrogen, store hydrogen, and so forth is there, it will be too late. Let me explain. Today, only 6% of the hydrogen produced is produced in a green way. All the rest is produced from fossil fuels. So it actually, hydrogen today, if you put it in a car, the most likely chance is that it actually contributes to climate change, does not improve climate change. Okay, so let's say if we would have today already massively deployed production of green hydrogen, and we would have already a hydrogen economy where we can transport and store and have charging stations of hydrogen around the cities. Even so, it would take 20 years from now to have that infrastructure and have car companies switching from electric vehicles and battery electric vehicles to fuel cell electric vehicles. So, and then convince the people that you have so hard tried to convince to use electric vehicles based on batteries that now they have to switch to hydrogen. So if you see just the market growth, I see that for urban electric vehicles, that won't be so likely. Although you see from time to time in the news that there are new developments and that it will get better. That's true, but it won't catch up with battery technology. And because batteries are not just in electric vehicles, they are used in so many other things, as cell phones and other mobile technology. So any developments in those technologies also benefits electric vehicle technology. But if we go into green hydrogen for other uses, let's say buses, trucks, planes, and ships, then there is a case to make. Even though, and we can have another time, another lecture on green hydrogen, there is another use of green hydrogen in which you combine it with other components, and you can make, for example, with nitrogen. If you mix green hydrogen with nitrogen, you can make green ammonia. And green ammonia can also be combusted, can be transported more easily than green hydrogen, and then that could be used for ships. Or you can combine a hydrogen with other stuff and make dimethyl ether, which is a gas. And then you can use that for cooking and heating, and that could replace natural gas in houses. So that's also very interesting. And then the one I find particularly interesting is if you capture CO2 from the air with carbon capture, and you mix it with hydrogen, then you have methanol. And methanol you can refine into kerosene and diesel, and that you can use in traditional vehicles and traditional buses, traditional cars, and traditional planes. So that would be fantastic, because then we don't have to change anything to our existing planes or existing trucks, and then we can make those green. Because then when they combust those fuels, the CO2 they are emitting from those fuels is actually the CO2 you captured. So you have a new CO2 cycle. Those are known as synthetic fuels, and also known as e-fuels, made from hydrogen. And I think it's better to pursue hydrogen in that direction for those applications that are a little bit lagging behind, rather than electric vehicles that are so advanced in terms of battery technology.
Great to hear about this insight, Dr. Samir. Today the whole EV battery environment depends on lithium ion. So
yes,
many of the countries, they don't have the lithium reserves. They don't have the sources of lithium in their country. and importing the same will add on to the cost of importing taxes and other things. What is your view on that? Will it be limiting the EV growth in countries where they don't have
Yeah,
lithium?
yeah, sure. Actually, I don't think, I mean, lithium is mostly concentrated in Latin America, in Chile, where I am from, which is good for my country, but and also Bolivia. So Chile and Bolivia are very big on lithium. But the thing is that even if we use most of the lithium we have, and by the way, lithium mining is very taxing on the environment for these countries, right? So it's not very good for our countries mining lithium in terms of environment. But the thing is that it is not a very costly material. So we import, export in a global economy, importing and exporting, depending on the economy of scale, it can actually improve the cost of something, right? So so for example, cell phones are very cheap, but we make chips in just 2 or 3 countries. We don't make microchips everywhere. So microchips are made in Taiwan and in the US and Europe. We don't make any microchips in other countries, right? So the economy of scale of doing stuff very well in some places is actually a beneficial from a cost perspective. So actually, it could draw the cost of batteries down. The problem with lithium is that there is not enough lithium for all the energy transitions technologies we need. So if we use lithium batteries for everything that we need to do energy transition, not just for electric vehicles, but we also use them on our phones and we also use them on our laptops, and we will use them in other applications as well. So lithium won't be cost effective enough in terms of a resource worldwide. So we need to find new battery technologies, and this is why everyone in the world is running to come up with the next battery. So you will, if you go into, I'm not an expert in battery technology, but you can see a lot of developments in solid state batteries and also other component-based batteries that don't take use of lithium. You have also sodium, sulfur batteries, which NAS and AS batteries, which are also getting more noticeable. So there are other battery technologies that can actually take over lithium in many other applications, which is what I think it will happen. So I won't be too much worried if you don't have lithium in your home country.
Great, Dr. Samir. Due to paucity of time, I think I'll wind up this Q&A with the last question. It's a coupled question. What do you see as prominent areas for young and aspiring researchers to see in this EV? And given your extensive work in both academia and along with industry, what collaborative opportunities do you see between research institutions, governments, and companies to advance EV charging technologies and ecosystem?
Well, my message to young people is that probably if you are studying engineering, whatever engineering it is, mechanical, chemical, electrical, whatever, this is probably the best time to study engineering. Why? Because energy transition to develop new technologies to mitigate climate change is actually a critical thing. So we are in crisis. It's a world crisis. The climate change. And when we have crises, is when there's more investment in development new technologies because we need to solve the crisis. And those technologies are made by engineers. So actually, if where you see more problems, those are the areas where you will have more jobs. So for example, if we see aviation will be a big issue, and shipping. So maritime applications and aviation applications, those are the ones we're really lagging behind. So if you are going to, and that's, you can be either a mechanical engineer and work in the mechanical aspects of the energy transition on those applications, but you also will need electrical engineers and electronics engineers and chemical engineers for the batteries or maybe the hydrogen and the other components. So my message for young people is just get into it, and hopefully if you have the talent and the capabilities, try to pursue a graduate study. So going to a PhD, a master and a PhD, because technology development is done at the high end of new knowledge. So therefore, I encourage you, if that's what you like, it's a very rewarding career. And then the collaboration with industry is the key. So one thing is to, when you do research like I do in my labs, if you do it in a void, if you do it just you by reading papers online, without having the insight from industry, you might be you might be lucky and looking in the right way, but also more certainly you will be looking in the wrong direction, because you might not be considering some factors that are key to understanding the application, where it goes from, where are some of the practical problems or economical problems or social problems or political problems that you need to also take into consideration. So if you do it in a void just from your field, even not talking to other engineers from other fields, then you're probably going to make an advancement, but not such an impactful advancement as you would do if you are in a collaborative environment with other people from other fields and industry. So I'm not saying that research shouldn't, there should be no inspirational research done without industry. I guess that's very good for basic sciences, for natural sciences, where they're really looking into revolutionary technologies and stuff that are not even in the scope of an industrial problem. But you have to take into consideration that climate change, we have set up goals for 2050. So this is not to make revolutionary technologies for another century. We need to solve this in from 10 to 20 years more from now. So this has to be done with industry, because those technologies need to be deployed, and they need to be deployed at the global scale and large scale to actually make an impact. Otherwise, it won't be of that much benefit to the problem we're trying to solve, right? So yeah, collaboration with industry is a key.
Thank you, Dr. Samir, for enlightening us with this, your wonderful presentation and addressing all the questions in detailed way. In fact, not just a relevance to this, both the iGen and iExplore, for all of us gathered here are somewhere connected with this, renewable energy or green energy for all our professions. Thank you so much for your time. And now I invite Mrs. G.K. Aarti, an active volunteer of iGen, to formally close the session with vote of thanks.
Yes, sir. First and foremost, I extend our heartfelt gratitude to your distinguished guest, Speaker Samir Kauro, for sharing your valuable insight and expertise with us today. Your knowledge and experiences have provided us with a wealth of information and inspiration. We are truly honored to have had you here. A special thanks to Dr. L. Ramesh, President of iGen, for organizing such a great event. A sincere thanks to our convener, Dr. M. Hagila, and also your honorary secretary in iGen for your meticulous planning and coordination. A thanks to moderator Mr. R. Navanitha Krishnan and also a director of iExplore Foundation for your hard work and dedication have ensured the smooth execution of this event, making it a great success. And also a thanks to co-convener Dr. P. Kanagraj, Assistant Professor in SRM IST, for making this research lecture series a memorable and impactful experience. We are also grateful to our participants and made the session more interactive and valuable. Lastly, I would like to thank everyone for ensuring all the arrangements were in place and that everything ran seamlessly. Thank you, sir.
Thank you very much for the invitation.
Thank you so much, Dr. Samir. Thank you. I think we can stop the live.
I apologize for my